Hello, everyone. Welcome to the Parsons Technical Webinar Series. I will be your host today, Jessica Bennett. Today, we have with us Lauren Turner presenting on bioaugmentation for the microbial degradation of 1,4-dioxane. We'll go through a few housekeeping items first, if we can go to the next slide. During the presentation, we'll be keeping all phone lines muted to limit background noise. If you have a question during the webinar, you can either enter it into the chat at any time, or you can hold it until the end to ask during the Q&A session that will be live or by chat. This webinar has been approved for 1 professional development hour or PDH credit. If you'd like to receive a PDH certificate, there will be a link to an attendance form posted several times throughout the webinar in the chat. There will be 3 multiple choice questions you will need to answer, so please take a look at those. And we will also post those in the chat in case you have any issues accessing that form during the webinar. And finally, this webinar is being recorded and will be posted on our YouTube channel in the next few days. So a brief agenda for today's webinar. We'll introduce our guest speaker, followed by a core value moment before we get into the technical presentation, and then we'll wrap up at the end with a Q&A session. So a little bit about our speaker, Lauren Turner. She's an environmental engineer that's been with us at Parsons for over a year now. She is supporting site investigation and remediation projects and objectives across the US. She's leveraging her research experience to support our internal R&D program for the remediation of contaminants, including 1,4-dioxane and PFAS. And finally, she has a PhD from Queen's University, Kingston, focusing on PFAS destruction. And with that, I will hand it off to Lauren for the core value moment.
Thank you very much. So here at Parsons, we have 5 core values as demonstrated on this slide: safety, quality, integrity, innovation, and sustainability. For today, I'm going to focus on innovation. Through a combination of technology and expertise here at Parsons, we look to provide solutions in a competitive market for clients to meet their needs and also to anticipate client needs. The innovation here at Parsons is achieved through collaboration with our multidisciplinary experts, partnerships, acquisitions, as well as the internal research and development program. The internal research and development program supports the investigation, identification, and optimization of technology surrounding analysis, characterization, and remediation of environmental contaminants in varying media. Some contaminants of interest for ongoing study include metals, polyfluoroalkyl substances, PFAS, and 1,4-dioxane, the topic of this presentation today. Investigative studies are conducted, including treatability work, which is supported by the Parsons Treatability Laboratory in Syracuse, New York, and the space there. This includes Parsons-funded research studies, collaborative studies with clients and vendors of products, as well as benchtop treatability studies for client sites. Moving into the content of the presentation, I'll start with some background just on 1,4-dioxane and into microbial degradation for 1,4-dioxane, and then I will discuss the study that was conducted bioaugmenting site media for 1,4-dioxane degradation. Starting here is a figure you may have seen before. We can see here it outlines domestic annual production, so that would be millions of pounds produced in the US, and this x-axis here is date. I've highlighted some years just on the bottom to clarify, as this text is a little small, and also some key events that are outlined here in yellow. So as we can see in the latter half of the 1800s, so 1,4-dioxane is observed to have been synthesized in the literature. We see manufacturing begins in the early 20th century, and then we see an uptick in production with this shaded blue area representing basically interpreted production, with these darker blue bars actually being data points of actual production volumes or pounds. We see in the late 1950s, 1,4-dioxane is used to stabilize 1,11-TCA. Primarily, 1,4-dioxane has been used to stabilize solvents, and that commonly being 1,11-TCA. It also is found often in the environment co-located with TCE. It is used in organic synthesis and polymerization. It's also been used in the manufacturing of ethoxylated surfactants. So in that case, it may be present as an impurity or a byproduct of the development of those products. And particularly the ethoxylated surfactants can be why there may be trace amounts of 1,4-dioxane in personal care products or cleaning products, as that was often a topic of discourse in the media around 1,4-dioxane in shampoo or cleaning products. We see the maximum production here is achieved in the mid-1980s in the United States, and a tapering downward with more investigation and understanding of the contaminant. And we can see here in the 2000s into the 2010s, there's identification of restricting the use and the identification of it being an environmental contaminant and investigation. Looking at the contaminant itself, I'll highlight some properties just to provide some context of how that contributes to potentially fate and transport as well as applicable remediation. The right side of the slide here has just some chemical structures. We can see that 1,4-dioxane is a cyclic hydrocarbon. It is highly soluble, most commonly referred to as just being completely miscible with water. Boils approximately at the same temperature of water. And then we look at partitioning into the vapor phase. It can do so primarily from the solid phase, although potentially not as readily as chlorinated solvents, for example. However, we do see the Henry's constant is quite low for 1,4-dioxane, which would indicate that it is not as likely to partition to the vapor phase when it is in the liquid phase. So when it's dissolved in water, less likely to go into the air, but 1,4-dioxane can volatilize from, for example, unsaturated soil. One thing to note as well is a relatively low log KOC. So with its high solubility and low partitioning to organic carbon, this suggests that it's not retained by organic carbon. So transport is going to be primarily dominated by effective transport, suggesting perhaps that groundwater plumes could be quite long, which may differ from some of its co-located contaminants, such as TCE or 111-TCA, which can be retarded in groundwater and not flow or transport or migrate as far. Looking here just at a schematic of it in the environment, it's just been a copy of a figure from ITRC with these same numbered parameters here just highlighted a little bit larger for visualization. If we look at this manufacturing building as a source, we can see in the environment can potential to volatilize, and then can enter the unsaturated zone or then the saturated zone in groundwater and have the capability to transport. Highlighted here are two potential destructive processes, so aerobic biodegradation, which is something that will be discussed in this presentation today, and then also photodegradation. I'll also highlight here phytoextraction. Phytoremediation has been identified as effective for 1,4-dioxane, and Parsons has experience implementing vegetation or trees in order to extract 1,4-dioxane from groundwater. Transport, again, primarily dominated by advection. We see potential then for aerobic biodegradation in oxic zones, and it can continue to transport through to surface water or certain receptors due to a limited absorption, and also the potential for diffusion into some low permeability zones. As a result of its impacts in the environment, ability to transport, and obviously known toxicological effects, there is obviously a demand for remediation for 1,4-dioxane in impacted matrices. The understanding of its potential carcinogenicity and general toxicity has guided agencies into develop screening levels or even some contaminant levels in certain states. However, there is no federal MCL for 1,4-dioxane. However, that does not mean the US EPA has not enforced remedial actions or demonstrated its authority in order to guide investigation for 1,4-dioxane and remediation. I will note that one thing to consider for 1,4-dioxane in terms of remediation is that the standards developed or regulations developed on a state level can often be quite conservative. You can see some of the states for which that is true include Colorado, Massachusetts, New Jersey, and Vermont, where these values are less than 1 microgram per liter. So this suggests that remediation not only needs to be available, but it also needs to be highly effective if your remedial goals are at these contaminant level regulations, MCLs. Touching again a little bit on properties to just compare it to potential co-contaminants and how that may play into remediation selection or challenges that need to be addressed. So firstly, if we look here, we've got the 1,4-dioxane properties and then commonly co-located with TCE, and then also it has been used with 1,1,1 TCA, so those values are here. We can look at that solubility is higher, but one thing I will note is the vapor pressure is a little lower for 1,4-dioxane, as well as the lower absorption or partitioning to organic carbon. And then also to highlight aerobic conditions are needed for biodegradation of 1,4-dioxane with current understanding. So when we look at remediating a site that potentially has 1,4-dioxane and other constituents, you have to consider that, for example, differing conditions. Anaerobic reductive dechlorination is heavily implemented and very effective for CVOCs. However, again, that requires anaerobic conditions, which would be in contrast of aerobic conditions for 1,4-dioxane, which could pose a challenge there. And then again, with the differences in vapor pressure, for example, a soil vapor extraction system would be, conventionally designed for CVOCs, and it can be applicable for 1,4-dioxane. But we see the emergence of the technique XSVE, which is extreme soil vapor extraction. So it may require some higher vapor pressures to pull the contaminant off of the solid phase relative to those other constituents. So looking here, this is also a figure from the ITRC, which just demonstrates available remediation technologies for 1,4-dioxane and generally where they are in terms of source zone through to dilute plume, with this more saturated orange being a higher concentration and this less saturated orange being lower concentration. As we can see, many categories are still within this emerging or less emerging to fully developed, although some are fully developed. But as we can see, when you do get into the dilute zone, we have monitored natural attenuation and co-metabolic bioremediation, which would be both biological remediation approaches and phytoremediation, which can do a wide range of concentrations, and then also pump and treat at lower concentrations. However, pump and treat can usually not be the first selection due to the amount of infrastructure and potential concerns or liability issues with bringing contamination out of the subsurface. However, we see metabolic bioremediation here is more focused in the emerging area as well as at higher concentrations. So that will be something I'll be discussing. And with any site, you'll obviously consider, concentration, the contamination depth, any cost prohibitive features, as well as, what zone it's in and the media itself. And as mentioned, there are less options for lower concentrations. However, when we think of a low concentration, we have to consider the regulatory values are even sub 1 microgram per liter. So considering how low is acceptable would definitely be a consideration, and what strategy can meet those goals. So just to touch again to highlight, the aerobic conditions are very important for considering biodegradation of 1,4-dioxane. However, aerobic techniques or the regime can be applicable for a wide range of applications depending on the specific process that's being looked at. I'm going to talk briefly about microbial degradation in general, and then I'll talk a little bit about metabolic and co-metabolic biodegradation for 1,4-dioxane. So in general, this is utilizing microorganisms and their enzyme systems to transform and degrade contaminants. Typically involves electron transfer processes to degrade and fully mineralize contaminants. These processes occur naturally and also are taken advantage of in many industries and applications, including wastewater bioreactors, soil, groundwater, and even in the oceans. There's been observed, naturally occurring populations that can help with degrading, for example, petroleum spills. As understood, applied, and practiced extensively is reductive dechlorination for CVOCs, which doesn't involve this anaerobic biodegradation. So then we'll look at aerobic biodegradation, which is applicable for 1,4-dioxane. So an aerobic regime requires, oxygenated environment, often represented by high amounts of dissolved oxygen in the water and a high oxidation reduction potential value, which can be measured and typically measured through water quality parameters. Oxygen acts as the electron acceptor, and the contaminant is the energy source of the electron donor that is then oxidized. This is applicable, obviously, for 1,4-dioxane, and then also petroleum hydrocarbons and things like MTBE. Looking at the anaerobic biodegradation, this is characterized and carried out in environments with low dissolved oxygen, typically highly negative ORP, suggests a good environment for anaerobic biodegradation. Hydrogen is an important electron donor. When we think of CVOCs, typically hydrogen replaces the chlorine atoms, and that's how that process continues. And then the contaminant itself is the electron acceptor, and that becomes reduced. This is applicable, obviously, chlorinated solvents, organometals, and also some pesticides and herbicides. Now, looking at more specific to 1,4-dioxane, we have the two processes here I'm going to talk about is metabolism and co-metabolism. Metabolism involves 1,4-dioxane being the primary source of energy for the microbes. So the concentration in available 1,4-dioxane essentially feeds the microbial species, such that a higher contaminant concentration will result in a more abundant energy source for the microbes to proliferate, which then leads to this being more applicable for high to very high concentrations, more food for the bugs to grow, eat, and then destroy the 1,4-dioxane. It's been commonly reported that high concentrations, so I'll use kind of this 250 micrograms per liter to represent higher concentrations, whereas lower here we see this is less than 100 micrograms per liter, and we can also think low in terms of regulatory standards that are, very low microgram per liter values. So this is kind of the key value that has been most supported by literature. Other studies are ongoing with lower concentrations. With the co-metabolism, the contaminant itself is not the sole energy source, so there will be another primary substrate that the microbes will consume for energy, and then as a function of that happening, the microbe needs to produce the necessary enzymes that have the capability to co-metabolize 1,4-dioxane. So this can be applicable for a wider range of concentrations, low to very high, as a result of the 1,4-dioxane concentration not being, the primary source of energy or supporting the growth of the microbes. Some other sources that can be a primary substrate for co-metabolism of 1,4-dioxane include propylene, toluene, and tetrahydrofuran or THF. And one thing is to consider, toluene, THF, these may be co-contaminants, so co-metabolism may be applicable if these are naturally occurring, but do you want to inject as another amendment THF into the subsurface, for example, for in situ remediation? So on that note, to further kind of discuss why metabolism is of interest to research and what benefit it can have, I'll get into some topics around that here. So it's currently understood to be, limited by low concentrations. Most studies identify, higher concentrations, hundreds of micrograms per liter, are sufficient for this technique. However, research continues to, investigate lower concentrations and determine, what is viable. And as mentioned, regulatory limits are quite low in groundwater and drinking water. So being able to conduct this process at low concentrations is very much of interest. And why so? That could be because there would be no additional amendment beyond the bioaugmentation of a culture if this was a bioaugmentation process. Additional amendments could require more infrastructure to inject. You're then going to have operation and maintenance costs, which could increase the entire cost of that alternative, which also could result in an increase in design complexity, potentially being a more cost-intensive solution. The potential risk if you are injecting something like a gas or another contaminant. So that is something to consider. So as I mentioned, co-metabolism would be, greatly advantageous if it's already co-located with something like toluene or THF, but it may not be ideal to inject that into the subsurface. Depending where you are, there may be challenges to, even inject that if you would even want to consider that as an approach. But bioaugmentation alone is a primarily passive approach, which can be extremely cost effective and also more sustainable and less disruptive to the natural environment. the bioaugmentation itself will augment the microbial population, but it may not have the infrastructure associated with something like an SVE system or in situ chemical oxidation. If permanent injection wells are used, and also something like ISCO, in situ chemical oxidation, could be a little bit more aggressive on the subsurface, having changes on potentially affecting the microbial population, killing it off, or affecting TOC or mineral speciation, which may not be ideal. So Parsons has, evaluated and experience with 1,4-dioxane sites, and that includes, investigation as well as remediation. That includes biostimulation of a naturally occurring metabolic microbial population. So there is a aquifer and a 1,4-dioxane degrading microbe. BERC1 has been identified to be existing on the site. However, it operates primarily in shallow oxic groundwater, and there are 1,4-dioxane impacts at depth, where the aquifer is more anaerobic. Therefore, an aeration system is being implemented in order to generate oxic conditions to promote the proliferation of that naturally occurring species to address 1,4-dioxane impacts on that site. I just want to touch on briefly that aerobic processes are understood to be effective. However, some studies have begun to, look into anaerobic biodegradation. It's not been widely understood to be applicable or seen as viable at this point in time. However, I just want to highlight that future research towards anaerobic biodegradation could be highly relevant, especially in situations where there are co-located 1,4-dioxane and chlorinated solvents. If they both were able to be degraded in the same regime, that could be highly attractive. And to touch here on some 1,4-dioxane degraders, as I mentioned, BERC1 has been identified from a site in South Carolina as naturally occurring, and several other sites have had 1,4-dioxane degrading species isolated from the media in their aquifers. This includes DXO88, which is a serum aerobic culture, and that is what is also being used in the study that will be discussed today. And then also, some may be familiar with CB1190. The approach, again, can be similar to enhanced reductive dechlorination, where you add the culture to the subsurface in order to induce or stimulate 1,4-dioxane degradation. And as mentioned, biodegradation, I think, can be highly advantageous as a remedial approach due to potentially being cost-effective, passive, and also with 1,4-dioxane, it can be further augmented or enhanced. For example, the Parsons site where aeration is being used or biosparging. So it can be kind of beefed up in a way as well. I'll now get into discussing the research study that was discussed. So that was investigated, and I'll just get through the basis of that in terms of study design and goals, as well as the methods and then results. So the key purpose of this study, I'll first start out with the site. This is a Superfund site in Colorado with pervasive 1,4-dioxane impacts. To date, there have been no identified 1,4-dioxane degrading species naturally occurring. And with respective to high concentrations being where metabolic biodegradation is applicable in the 250 range, the site concentrations are low comparatively to that. So we are looking at concentrations at 10 and 50 micrograms per liter for this site. So the key objective was to, investigate bioaugmenting site media for 1,4-dioxane degradation to determine if there is some viability with the media on site, groundwater and soil, and if that could potentially meet the client needs and identify a remedial solution that is sustainable and cost-effective. Particularly for the study, I wanted to know if the culture was compatible with site media, and also looking at the concentrations, despite it being understood that metabolism works faster for higher concentrations. Even at these lower concentrations, is it worth further investigation and considering as an alternative? So as I mentioned, DXO88 is the serum culture that was used. It's an aerobic culture. It has the capability for metabolic and co-metabolic 1,4-dioxane degradation with propane being used in co-metabolic processes as the primary substrate. It was enriched from a 1,4-dioxane contaminated site in California, and serum has demonstrated bench and field testing for both metabolic and co-metabolic applications. So we're very grateful for the collaboration and support of serum with the culture. And as we can see here, the culture being shipped, perhaps different than ERD applications. We see there's headspace with the culture as it is an aerobic culture. And here is just a little image of the culture on its like mineral substrate when it was received in lab. So it's in a 200 milliliter glass serum bottle, and it's kind of clipped up all together. It's kind of hard to see, but it's kind of in this little gray mass that you could see if you're looking in person. Looking at the study design itself, so I will mention that groundwater and soil were collected from background locations on site. So this was unimpacted media that was spiked to the desired concentrations in the laboratory. This was done as there are other contaminants on site. So although for applicability to those locations, you'd want to understand co-contaminant effects, we wanted to look at specifically the media and 1,4-dioxane without having any issues of not being able to deconvolute if it was perhaps a media compatibility option or contaminants that were inhibiting degradation, as well as some contaminants with 8260 could drive up the reporting limit or detection limit. So this would allow a more refined look in that capacity in terms of analytical. For the treatments, we had controls, which include a poisoned or killed control, and then a native control, which just was out without any bioaugmentation. The poison control was basically designed so that you prevent any microbial activity or kill any microbial activity existing in the media. For the active treatments that were bioaugmented, culture addition was conducted based on recommended doses by serum. There were two concentrations of 1,4-dioxane, around 10 micrograms per liter and 50 micrograms per liter. The active treatments were conducted in triplicate and sampled in triplicate, and the controls were performed in duplicate and sampled in duplicate, and sampled at less frequently than the active treatments. The total experimental period was 90 days, and there was a temporary period of active aeration that was implemented. We can see the little setup here. There was an air stone in place that air could be injected into the bottle as needed. There was soil here on the bottom, as well as groundwater, and then headspace, and then some fittings and filters in order to sample and keep the study going. So these were continuous bottles, not destructive bottles, such that when one was sampled, it was done with. Key parameters for performance monitoring include obviously a 1,4-dioxane analysis, and that was conducted via US EPA 8260 SIM, single ion monitoring, and then key considerations, obviously dissolved oxygen and ORP, which are indicative of what kind of conditions you have in terms of oxic or anoxic. So getting into some baseline conditions of the media itself. Firstly, just to point out for the soil in the killed control, this was autoclaved in order to sterilize it. The soil was sampled at baseline using a synthetic precipitation leaching procedure, SPLP, in order to investigate, and confirm that there were no impacts in the soil as it was from a background location. And then also it was sampled again for SPLP 1,4-dioxane, where the leachate was analyzed via 8260 in order to assess, mass balance closure and consider if there's any partitioning to the solid phase, which would not be expected for 1,4-dioxane based on its properties, but it also was just to kind of close the mass balance. If we look at our treatments, I will highlight that, pH was consistent through all bottles as expected, all the same source water. The temperature was consistent, and throughout the study, it was reflective of the laboratory space temperature. And then we have the dissolved oxygen concentration and ORP. These were relatively consistent throughout treatments. However, I will highlight in the killed control, mercury chloride was used to poison the bottles, and as a result, that can be an oxidant in the water. Therefore, we see some elevated DO and ORP as a result of that amendment. So that is to be expected. We begin discussing some results, and here I will first kick off with the water quality parameters. So based on the dissolved oxygen and ORP, highlighting here the kill control, which was higher as a result of that amendment to kill microbial activity, the pH remained between 7 and 8, anaerobic conditions were maintained. We see throughout the study above 4 milligrams per liter, DO, and then ORP above 200 millivolts for the duration of the study. The temperature, as mentioned, was consistent with any fluctuations in the laboratory temperature, and general fluctuations in DO could perhaps be related to some temperature fluctuations, as this was conducted in the winter through the spring, where here in the Northeast, temperature jumps up and down quite a bit. And depending on temperature, sometimes it will affect the amount of oxygen that can be dissolved in the water. It's basically saturation limit. So starting off, things look pretty good and aerobic in order to support our aerobic culture that was added to our treatment bottles. First here, I will present the 1,4-dioxane results that were in water through 45 days of study. So we'll start off here with the figure. I'll identify these two lines, the orange and pink, represent our controls, both the native and killed control. Through 45 days, the variability was pretty limited, and results suggest there was no loss in the controls throughout the first 45 days, which then, if you compare to the active treatments, can be used to suggest that any degradation are a result of the bioaugmentation. So this blue line here represents the higher of the two concentration explored, about goal 50 micrograms per liter, and then this lower green line is the lower concentration explored. Firstly, if we kind of just look basically at the slopes connecting these data markers, we can see greater reduction in the 50 microgram per liter goal spike, reflective to this lower concentration, which based off of what is understood for 1,4-dioxane aerobic metabolic degradation, we would expect a higher concentration to be more effective, essentially, for aerobic metabolic degradation. And we'll look at these circles here, which kind of just represent the ANOVA or statistical analysis conducted. So an analysis of variance was conducted to compare the bioaugmented treatments to the controls where they were both sampled. So that included 20 days and 45 days. Basically, this compares sample means within the treatment itself and then between treatments to identify if there is suggestion of statistically significant difference between the concentration of controls and the concentration of the bioaugmented treatments. The 50 microgram per liter treatment was conducted based off of concentration values, but obviously the controls were at a higher concentration than the 10 microgram per liter bottles. So these results the ANOVA was conducted on results that were essentially normalized, C over C naught, or relative decrease, to try to get some assessment of if there is statistically significant difference between the active bioaugmented treatments and then our control treatments. If we look at the 50 microgram per liter bioaugmented bottle through 45 days, this green here represents that the ANOVA suggests at our confidence level of 5%, 0.05. So the p-values for both of these ANOVA points was less than that, suggesting there was statistically significant difference between the controls and the treatment bottle, suggesting degradation was occurring. And by day 45, we see about 33% reduction in 1,4-dioxane concentration. Looking at the 10 microgram per liter bioaugmented treatment, the ANOVA did not suggest there was a difference by 20 days between the control and the bioaugmented treatment. However, by day 45, it did suggest that looking at relative concentrations, there was a difference in this concentration reflective to the controls. And that was basically an average concentration decline of 17% in the 10 microgram per liter treatment. So through 45 days, we see that the microcosms have been maintained at aerobic conditions and biodegradation is presumed to be observed. Now, as I mentioned, there was a brief period of active aeration that was implemented. So there was increased variability after aeration, and I'll discuss some potential causes for that. But first, to talk about the motivation. Although, DO appeared to be good, degradation was, slow. So there was the consideration of, is this solely like a concentration effect, or if we could maybe boost the DO even higher, would that perhaps increase the degradation? The culture itself can be grown and thrive very well at 6 to 8 milligrams per liter DO, which may not be applicable in situ without any aeration. However, it was something we wanted to investigate. So this shaded period represents when aeration was implemented, and the sampling periods during and after aeration were 60 days and the 90-day treatments. So as we can clearly see with these values, when aeration was implemented, there is loss in the controls, as well as looking at the error bars, the variability between the bottles within treatments also very much increased. So as a result of this, and as we can see even here, we'll note the native control loss was even lower than the 50 microgram per liter bioaugmented treatment at this point. So using this data, we cannot evaluate whether there's any difference. We can't deconvolute any effects of biodegradation and then artifact of the aeration. So we can't make any strong conclusion about increased degradation between the 60 and 90-day sample. And as a result of aeration, this could be due to potential volatilization, even though a low flow rate of air was attempted to be used. Could be to some inconsistencies in the tubing and connections and just checking things there, as well as air stones, potentially some small variabilities, as we really want them to bubble very finely to get air into the water. And all air stones were not 100% identical, so it could have had some effects that would definitely be considered if future work is conducted. Just again to highlight some things that were going on with the controls. If we look here, I've got the native control on the left and the killed control on the plot on the right. So even at day 45 in the native control, we do see a little bit of increase in variability. However, that increases after aeration is implemented through day 60 and day 90. And by day 90 in the control, we do see significant loss, suggesting, it was compromised or affected by aeration. And it was also observed in the killed control, less variability here at 60 days, but it does increase by 90 days and due to, loss in both the native and killed control. I would not suggest that, any reduction in this native control is somehow a phenomenon of another microbial species acting to degrade 1,4-dioxane. However, no microbial analyses were done to kind of elucidate that further. So again, as mentioned, we have 1,4-dioxane in soil, which was analyzed. He did the SPLP, and then the leachate was measured. And again, day 90, it was not detected at the detection limit of 0.57 micrograms per liter. So it was not in baseline soil, and it was not in the end soil, which, consistent with contaminant properties, there was no retention of 1,4-dioxane in the soil, which is to be expected, but it also supports that concentrations of 1,4-dioxane in the groundwater were reflective of all 1,4-dioxane concentration in the treatment bottle. So again, essentially no evidence 1,4-dioxane is in the solid phase, which is to be expected, but this is obviously a check that is needed. Now I'm going to summarize, the study finding itself, some outlook looking forward, and then some conclusions and identify some data gaps as we conclude this presentation. So degradation was observed. Although most of the literature and studies available suggest that higher concentrations, such as hundreds of micrograms per liter, are most ideal for aerobic metabolism of 1,4-dioxane, we did see, good percent of destruction. So it was a 33% reduction in 1,4-dioxane concentration by 45 days. And the percent degradation was lower in the 10 microgram per liter spiked bioaugmented treatment. However, it still was 17%. Studies are ongoing, such as some work that was presented recently at the Battelle Bioremediation Conference with lower concentrations being investigated, consistent with the study that do suggest that metabolism could be applicable for lower concentrations of 1,4-dioxane, and the benefits of this potentially being a passive and sustainable approach for lower concentrations are definitely something worth investigating to meet clients' needs and solve the issue of 1,4-dioxane in groundwater. We did see, again, greater degradation in the higher concentration. So we did see some rate observed effects related to the concentration, which again is to be expected based on what is understood and the literature. We did see that our aeration in this study did not improve degradation in the study, and we did not really see a spike in DO through the tools we used to measure it, which could suggest perhaps it was an influence of the DO meter or the systems itself, that DO really was as high as it could be in the bottles. However, I want to note this is reflective of this study, and it's observed and well understood that it can be effective in other work, such as Parsons site, where the aeration trench is being implemented to kind of convert areas of the aquifer from anaerobic to aerobic in order to take advantage of the naturally occurring 1,4-dioxane degrading species. So the unaerated conditions in the bottle, as well as the soil and groundwater within the bottles, appear to be very suitable for 1,4-dioxane degradation, which suggests this would be a strategy that is worth investigating further for the specific site, and maybe potentially continuing into a pilot study to determine certain parameters or optimize the application of metabolism for 1,4-dioxane. So I want to touch here on outlook. So as mentioned, I would really want to highlight low concentrations. Commonly, the thought is not as ideal for metabolism. However, I think this does suggest there is a viability and a need for future study to refine this application and see where the true limitations are in terms of 1,4-dioxane concentration in groundwater. Again, repeated bioaugmentation with the option to also modify this future studies could be beneficial. It does suggest that for the site specifically, it's definitely worth investigating. And as mentioned, even if it is lower compared to higher concentrations, we look at 33% in 45 days of degradation. And even if the degradation rate slows further as concentration is reduced, when we look at remediation strategies in general, 90 days is 45 days or 90 days is a very short time frame, with many active strategies taking longer than that. And then even considering MNA, the remediation timeline to meet cleanup goals can even be decades. So even if it's relatively slow for metabolism based on 1,4-dioxane concentration, it may not be slow when you put it into perspective of available remediation alternatives, and especially considering the advantages of being a passive approach, and also potentially a sustainable approach that is environmentally attractive. So the results from this study can also inform future studies and generate some new data gaps that are worth investigating. So for example, a longer study duration could be highly advantageous. The culture concentration could also be investigated. There could be looked at the sensitivity to more or less culture based on concentration of 1,4-dioxane used. It would definitely be relevant to look at impacted site media and co-contaminants. There are potential for other co-contaminants or subsurface conditions to inhibit 1,4-dioxane biodegradation, and particularly with chlorinated solvents or TCE being co-located with 1,4-dioxane impacts, it's definitely relevant to consider if they can inhibit degradation, which it is known some concentrations of things like 1,1 TCE can inhibit biodegradation. So definitely worth considering how that will affect the viability of this technology for certain sites. And just to begin wrapping up, I really want to highlight that microbial degradation of 1,4-dioxane is still continually evolving, as noted on that earlier ITRC figure. It's kind of still in the emerging phase. However, there are plenty of studies both in the literature at the bench scale and field scale implementation and pilots that continue to develop and improve the understanding as well as demonstrating effectiveness of biodegradation for 1,4-dioxane and especially metabolism of 1,4-dioxane. Further investigation for aerobic biodegradation, particularly metabolism at less than 100 micrograms per liter, will continue to fill knowledge gaps and provide solutions for contaminated sites to meet remedial goals and to meet client needs. And any development which can support a passive remediation approach or M&A of 1,4-dioxane will generally be more cost effective and environmentally sustainable, which may be attractive to your client or to a regulator. So this is definitely something I think is very important to continue investigating, particularly with some remediation strategies being less effective or requiring a little bit more infrastructure or higher rates, such as extreme SVE. If you need to have a higher vacuum pressure, it may be more energy intensive, which could potentially drive cost up or result in longer remediation timeframes. And future work is proposed to be conducted at the Parsons Treatability Lab to develop solutions and meet client needs. The lab space in Syracuse at Parsons is a great space in order to investigate contaminants and their remediation. And we're always happy to further develop technologies and work with clients if they have impacted site media to develop how we can support them and find new solutions in order to address challenges that seem to be ongoing in environmental remediation. So I want to say thank you for your attention. I'm available for some questions. Thank you.
Thank you, Lauren. That was a great presentation on some of the latest research on 1,4-dioxane biodegradation. This is really exciting results to see. If anyone has a question, you can enter them in the chat now and we can go through them. If there's anything that we don't get through today during the Q&A session, please feel free to reach out to Lauren directly. Her contact information is on the slide here.
For sure. I think I see one in the chat.
Yeah, looks like we got a few coming in. So let's see, the first one is from Taylor Schweigel. What makes biodegradation for 1,4-dioxane and groundwater desirable, and what challenges exist for other technologies?
Absolutely. So as mentioned, like a passive approach, I think would always be ideal. It can be cost effective and sustainable to implement that kind of technology. As mentioned, some challenges for other technologies could be, extreme soil vapor extraction, which could require more infrastructure. Something like in situ chemical oxidation can be very harsh or more aggressive on the environment, affecting any subsurface characterization, mineralization, total organic carbon content. So that could be something that's not ideal, depending on the local receptors or what else is going on in the subsurface. So I think a sustainable approach that can be passive is definitely ideal for the environment, and also makes it cost effective. I'll just go through what we have here. Again, to further investigate, I definitely think longer studies, different culture doses, investigating co-contaminants, particularly those relevant to the certain sites. For example, this site that was investigated here would be necessary, and not only to observe 1,4-dioxane degradation in these conditions, but also maybe understanding how your analytical methods hold up if 8260 is looking for or being infected by more contaminants. If that drives up detection limits, what are your detection limits relative to cleanup goals, and how can you further address and optimize that? We used unimpacted site media just to look specifically at the media in 1,4-dioxane without considering co-contaminants for the tying into the last question, to think about one, detection limits, if that would be influenced by co-contaminants, and also just so we could really focus on just the media and the 1,4-dioxane instead of having to deconvolute if any effects or the trends in degradation were influenced by the co-contaminants. Microbial degradation for 1,4-dioxane can be inhibited by constituents in the subsurface, as well as subsurface conditions. So obviously, if you have an anaerobic subsurface, that's obviously not going to be ideal. It will inhibit these microbial species from acting. Metals have been observed to potentially inhibit 1,4-dioxane biodegradation, as well as some chlorinated solvents, including TCE or 1,1-DCE. That can be an impact. Also with general microbial degradation processes, super low pH or very high pH is obviously not going to be super suitable for microbial species. If you have a really cold temperature, that will not be super ideal for supporting a microbial population as well. And also to tie into future work, I think, as one of the questions here notes, we did not do any microbial sampling, but that's something that we're definitely considering moving forward in order to assess what genes, so the microbial population itself, as well as its abundance throughout the study. So to give us the opportunity to investigate what is there, and then if it is increasing. The issues with aeration, I definitely think could be investigated in a few ways. One, to really just refine the laboratory setup. I think it's important maybe to check all your connections, make sure the tubing is consistent in sizing and air delivery is consistent. We were splitting airflow from different pumps. So more consistent air source or a manifold could be something to look at that. I also think if, volatilization is occurring, there are ways to capture and quantify also. So some potential vapor trap or air trap that is able to be measured could then, tie in the mass balance consideration and further support investigations there. In some instances, if co-contaminants or at concentrations that can be inhibited to microbial degradation, then I would say, yes, co-contaminants could reduce the effectiveness. I think a lot of the concentrations that are inhibitive are quite high for metals into like high microgram per liter, hundreds through to ppm levels. I did see, some literature that suggests similar concentrations like that are also for CVOCs, but I think recently see an abstract where I think it was 13 micrograms per liter of 1,1-DCE was observed to have an inhibitory effect, but only within like the first 10 days of the study. So it slowed the initial degradation, but it then kind of was able to catch up. And I think that was for BERC1, which also I think could also co-metabolize 1,1-DCE as well. So that's definitely something that would be worth looking into. As far as native and killed control preparation, the native control was just the groundwater and soil. So it was prepared the same way as the augmented treatments without the addition of the culture. And then for the killed control, the groundwater was spiked with the mercury chloride, which is killed control, and that was pulled from the literature, a study that had also used that effectively as a poison for the water. And then the soil for the killed control was autoclaved in order to sterilize, and then all lab materials used in the study were either autoclaved or sterilized with alcohol if they were too busy or too big for our autoclave size. The spike goal was 50 micrograms per liter, 50 ppb, but the concentration did come to lower, as you can see, 42 ppb. And that's just a little variation in concentration. The goal spike in order did not meet, the exact theoretical concentration. Working with lower concentrations, you're trying to, really rely on your small volume pipette to be super accurate. 8260 SIM was used instead of 8270, sorry. This was primarily focused just on sample volume needed. 8270 requires a lot larger sample, and we use 5-liter bottles. And the one sample is 3 40 ml BOAs for 1,4-dioxane. So we would need essentially just a very large setup and a lot of impacted media, so that was a less viable method to use for this benchtop study. But I know 8270 is often used in the field, especially with low concentrations. In terms of cross-contamination, we didn't do any microbial sampling, and we only sampled for 8260. So I would say results up to 45 days do suggest that things look good, but I think that would be also another consideration moving if you look at the aeration period. Even though there were filters for the air that were very fine, it is possible with the aeration that there was, some type of contamination or other interference. However, given the specific site that media was used from has pervasive 1,4-dioxane impacts, and no naturally 1,4-dioxane degrading species have been identified. I think where my head is going with this question is that was something else introduced that could have degraded 1,4-dioxane. I think it is unlikely, but obviously not impossible. So a further microbial analysis or a larger analytical suite definitely can help elucidate and define and answer some of these questions.
Well, thank you to everybody for all the great questions. As I mentioned, if there's anything else you'd like to follow up with Lauren, please reach out to her directly. If we can go to the next slide. So our next webinar will be on August 13th at the same time, presented by Natalia O'Connor on reductive defluorination of PFAS using a UV photochemical reactor. A link to the form for a PDH credit has been posted in the chat a few times. If you have any issues downloading or accessing that form, just please let us know and we can help you out with that. And if you missed any of the questions on that form, there will be a recording of this webinar posted on our YouTube channel in the next few days. Thank you to everyone who joined us today for our webinar, and we hope to see you again in August.
Thank you.